All right, so now let's think about memory. Um, we can use the latches and the flip-flops that we looked at earlier to implement memory. So your book offers a simple model of a memory element that's built around latches. Now, we still have our clock and our data as well as our cue outputs. All right, so we have our latch. And what we do know about our latch is that when clock goes to 1, it will go ahead and take in whatever bit is there at the D or the data input. Now, let's think about how this is put together. We have a 2 to 4 decoder. And with that 2 to 4 decoder, um, he's going to accept two inputs, such as a 0, 0, 0, 1, 1, 0, or a 1, 1. Those are the four possible inputs. And if it's 0, 0, then 0 is turned on, and everybody else is turned off with zeros. Now, if 0, 1 is kind of presented to the address lines, then that means this one is a 1, and everybody else in this case is turned off, right? So that's standard decoder functionality. So let's think about this from, let's say that we put in a 0, 0 into our quote-unquote address lines. So everybody else will output zeros, which means that AND gate. So if you put in 0, 0, only one of these guys will be 1. All of these AND gates will have zeros at the output, and only one of the AND gates, the very top one, will have a 1. And he will have a 1 only if we signal with the right enable to go ahead and output the 1. So the AND gate will act as a gate. He will only allow the input to be reflected at the output when there is a signal here, the right enable. Right? So only when he's signaled here. And if we do select that AND gate, and if we do say right enable, a 1 ends up going into the clock of both of these two latches. And so what comes out will be a value that's a 2-bit value from the left and from the right. And that value that comes out will be whatever was stored in there. So we have the ability to go ahead and select one of the banks. So this top bank would be 0, 0. This bank would be 0, 1, 1, 0, and 1, 1. And then we can select one of them. And once they are selected, we can also, with the right enable, take in inputs from DN. Let's call this one DN sub 0 and DN sub 1. I think this is, if you look carefully, you'll see that there's a small typo that says DN1, DN1, and it should be, actually this one here should be DN sub 0. But that is the data that will be written to our latches. And it will be written only when the C input goes from 0 to 1. And the C input will go from 0 to 1 only when the 2 to 4 decoder has given us, when it's selected the correct, or this particular bank, the correct bank, and we also have the right enable. So that will allow us to implement a memory element. So the 4 indicates we have 4 addressable cells, and then the 2 where we have this x4, x2, the 2 indicates that the size of the word is 2 bits. So, and so in this case, it's a 4 by 2 static RAM. So there are 4 elements, each one of them, or 4 places for values, each one of them 2 bits in width. So that's the word size. So that is a review of that static RAM. And that static RAM holds its value as long as there's power. If you remove power, then it will actually just lose its value. Dynamic RAM has it involves an energy storage element called a capacitor that has to be refreshed. It serves kind of like a battery backup, but you have to refresh it to make sure that it holds on to its memory. And that periodic refreshing is the dynamic element, hence dynamic RAM. An actual data sheet for a static RAM could be found if you did a search for the 2114. This one has 1024 separate 4-bit words. And so that one would give you a peek at actual RAM. And then notice, though, that there is a write enable. So when that write enable signal comes in, this guy will take whatever data is being presented here and write it to memory. So write enable is our 0 to 1 clock / reg write input, and it'll take that information and write it. And where it'll write it will depend on your address lines. So if you think about what we're looking at here, our address lines are labeled A0 through A9. So there are 10 address lines, which means there are 2 to the 10th equals 1024 different cells that we can write our data to. So 1024 different memory elements. Each one of those words would be 4 bits in width. Also, notice that we can write in data, and if we don't signal to the CPU that we want to write, then we're doing a read. And so in this case, we would be looking at our data lines. So we can control whether we're writing or whether we're reading from memory, but it's a dual port. So we're going to use the same lines for both data, dropping in data, but also when we wish to read data, we could use those same lines. So this is a bidirectional element. And so that memory is modeled in your textbook in this way, where it shows that we have, in this case, we have 21 address lines. And so 21 address lines, if you think about it, 2 to the 21, that corresponds to the number of words. That's 2 to the 21 words. And each one of those words is 16 bits in length. Now, when we're ready to actually look at the output, we could enable the output. And when we're ready to write information in, we could use a write enable to take in information. So this one has separate. This is not bidirectional. You have separate input pins for writing in information, and then for reading information, you have separate pins for that. So that was a review of how we could model memory and develop some intuition about how memory works. Next thing we'll look at is the program counter and how we can interface the program counter to work with memory.